Awesome. Well, thanks everyone for coming again to the Cryptography Talk series. Just a quick reminder that this talk is being recorded and it's going to be on YouTube, on our YouTube channel afterwards. So if you have some questions that you don't want to be in the recording, I highly recommend asking them at the end of the talk rather than during the talk. Also, if you are not normally getting these invitations to this talk series, you can join the Cryptalk alias on IDWeb, or I'm not sure what they use these days, if IDWeb even exists anymore, but maybe it exists. But yeah, so join the Cryptalk alias and you'll get these notifications and invitations every time. All right, Melissa, you should go ahead with the intro and then we go from there.
Hi. So today we're really happy to have Amey Shukla from the University of Connecticut here to give us an update on the latest work that he's been doing with fuzzy extractors. We also have his advisor, Ben Fuller, in the audience to help out with questions, which is great. Yeah, so they've been sort of on the forefront of the fuzzy extractor research line, and so we're very excited to hear the latest on what they've been doing.
All right. Hi, everyone. My name is Amey, and this is Fuzzy Extractors Are Practical. And this is joint work with Sohaib Ahmed, Sisha Chen, Luke Demarest, Benjamin Fuller, Caleb Manicky, and Alexander Russell. So really, before I start giving this talk, I want to give you a little bit of a promise of what I'm going to talk about in this talk. So during this talk, I'll talk about, well, number one, how to do cryptography with biometrics, which is kind of the main point of using fuzzy extractors. And then this evolving story of security of cryptography that's built for biometrics. And then I'll show you how to derive usable keys with high entropy and high true accept rate for these biometrics. I'll talk a little bit about why does this whole thing matter in the very first place. And near the end, I'll show you our results where we are able to get 105 bits of entropy at 92% true accept rate, 83 bits of entropy at 98% true accept rate. And this is in comparison to previous work like SSF19 and ZCY21, where they had much lower entropy at about 60% TAR. All right, so first I'll talk about biometric key derivation. So I don't think many people would argue with the fact that passwords are kind of problematic because, all the time you hear that data breaches happen. In fact, I really love this one data breach called RawQ because, it had 32 million passwords leaked. And now they actually use this in universities to teach university kids how to, crack passwords, essentially using something like Hashcat or John the Ripper. And it doesn't matter how good you are of a cryptographer. You can't control when a data breach happens. So here I have a screenshot of my advisor's have you been compromised account where, his passwords is in, one breach. And there's Alexander Russell, who's even more senior cryptographer, whose password is in like 12 breaches out there. And, with passwords, I like this XKCD comic, which says that, like through 20 years of effort, we have actually successfully trained everyone to use passwords that are really hard for humans to remember, but very easy for computers to break. And so this really raises this question, is there anything better than passwords out there? So maybe we can use biometrics. Now, I used to have a slide here where I would say why we should use biometrics, but frankly speaking, nowadays, everyone is using biometrics to unlock their phone, whether you're using Android or you're using iOS. But not all biometrics are built the same. So we have some requirements we want from our biometrics before we use them. So for example, these biometrics should measure a unique physical phenomenon about you as a human being that's unique to you. They should be easily collectible. So it should not be like blood tests where you scan the DNA of a human being because that's obviously not practical. They should be permanent, so they should not change over time. They should stay somewhat constant, and they should be universal, which means that every human being should have these biometrics because frankly, if you're deploying all this infrastructure, well, everyone should be able to use it. Now, unfortunately, with biometrics, repeated readings actually exhibit significant noise. So what I mean by this is that, let's say I take a picture of my iris, and then a few seconds later, I take a second picture of the same iris. Now, the problem here is that the second picture might be slightly different from the first one because, there's maybe lighting towards your eye. Maybe you woke up on the wrong side of the bed, so now your eyes are really red, or maybe your eyes are a little droopy because you're sleepy in the morning. many things, and these small changes in the image, even though it belongs to the same iris, can make things really difficult. Now, this ratio of uniqueness and noise varies widely between different biometrics. And from all the biometrics, iris is believed to be the best. So for the rest of this talk, we are going to focus on irises. Unfortunately, unlike passwords, you can't afford to lose biometrics. Because imagine the same scenario where a data breach happens and your passwords get leaked. Well, it's kind of sad, but you can use the power of your imagination to come up with a new password and then you're fine. And then just hope that the new data breach doesn't happen again. But with biometrics, if your biometric is on the internet for everyone to see, you can't use that biometric ever again because unlike passwords, you can't use the power of your imagination to come up with a new eyeball or a new fingerprint or a new face. It's gone forever. Now with passwords, fortunately, we have a tool called hashes where you don't really store the password raw in a database. You store a hash of the password. And so even if it gets leaked, as long as you had high entropy of a password, which you probably don't, but if you did, it's computationally infeasible to invert it. But this is not possible with biometrics because the same thing I just talked about with biometrics having noise between different readings, the hash function will just have an avalanche effect. And even though these images are very similar, the avalanche effect will make them look completely random. And so it turns out the best tool we have to protect our passwords, which are hashes, is not applicable to biometrics. And so we need to figure out a way to secure biometrics. So fortunately for us, this problem has been studied for almost 3 decades at this point. And this whole idea of doing cryptography with biometrics was introduced as fuzzy extractors in this paper by Doris, Ostrowski, Raisin, and Smith. And they come up with a really clever idea here, which is that, hey, if what's stopping you from doing cryptography with these biometrics is that there's significant noise between different readings, how about we use error correction to correct the noise, and then we can do whatever cryptography we want because now we can output the stable key every single time. And this is fantastic. So I'll talk a little bit about their algorithm here, and then I'll show you why this doesn't work. So they have this enrollment algorithm called GEN, where they create a key from the initial reading of your iris or any biometric, and it generates a public value called helper. And now, obviously, attackers should know nothing about the key because that's kind of the whole point of doing cryptography is that if the key is out there, then it's game over. Now you have this algorithm called rep, which is for authentication, that produces a key if the distance between the initial reading and a final reading is below some threshold t. And using helper, it will output the exact same key that you were able to generate using gen. Obviously, the key should look like a random string, and the helper should not cause leakage even when the device is compromised, because this helper is actually a public value. So you should be able to put it anywhere, on the internet, anywhere. And this should not cause any leakage. So this is a requirement of that fuzzy extractor, and I'm going to ask, is the problem solved? And the answer is obviously no, because I won't be here giving this talk. And so it turns out that for the entropy/error regime that's present in biometrics, traditional fuzzy extractors based on error correcting codes actually give you no security at all. So it turns out that fuzzy extractors are very picky with how they work. So traditional fuzzy extractors, like I said, use error correcting codes to deal with noise. Unfortunately, when you use these error correcting codes, you need to write down some information in the helper that will help you with, getting the original input back. Now, unfortunately, if you have to write down more information, then there is entropy in the whole biometric. It turns out that you just gave your adversary the biometric in full in just a convoluted format that they can decode and then get the biometric. And so this actually provides you no security. And this whole regime where you have no security when the number of errors is greater than the entropy of the biometric is called more errors than an entropy. And this is something that has haunted our field for quite a while. This whole thing is actually kind of sufficient when you have biometrics that are independently and identically distributed or have almost full entropy for their length. Unfortunately, I do not know of any biometric that satisfies this. And plenty of papers out there have made this assumption without any statistical justification on this. Now, before I talk more on this, I would like to talk about this thing called entropy of a biometric and how do we measure this. So to do this, we use something called a Dogman entropy test, which was part of this. Yeah, I'll answer the question.
Okay, cool. Thanks. I wanted to ask, in the previous scenario, like with the error correcting codes, is that sufficient for the case where, like the sketch that the verifier needs is stored kind of locally on the user's device?
So if you're assuming that the sketch will not get leaked from the device, then yes,
Okay.
that's an assumption you have to make. Yes. So you're assuming that the helper value never leaves the machine, then yes, it's completely secure because there's nothing for attacker to obtain information from.
But I guess I'd also argue in that point, you might as well do what we do now, which is just store an original reading in trusted hardware, and if it's close enough, you output a key. Right. So that the security model for storing an original enrollment and like hoping helper doesn't leak are roughly the same.
I see. So, okay. And so in your work, you're targeting a case where the helper is sent off to a remote server and is really truly public, or considered to be kind of public. Okay, got it.
Yes. All right. So we use this entropy test by Dogman, and I'll explain this in detail in a bit, but how it basically works is that you fit the unlike distribution to a binomial. And in their paper, they were able to get 249 bits of entropy for iris, which is actually the strongest entropy estimate for a biometric so far. And error rates of this of the biometrics are between 10 to 35%. And I'll explain what all this does in a couple of slides. All right, so let's take a look at this histogram that I have up. So the left side of the histogram means the Hamming distance between readings of the same iris. So for example, on the right side, I have 3 courages. And even though they look slightly different, it's the same good boy courage, which means that it's the same iris. And so this left side of the histogram impacts the true accept rate. So the closer this distance is to 0, the closer the readings are to each other. In fact, if this was completely 0, you don't need to even use fuzzy extractors because the key will always be the same. Now, the right side of the histogram is the unlike distribution, which is the Hamming distance between different irises. So here again, I have Courage and Tom, and even though they're both good boys, they are different 2 boys, which means they have different irises. And this is the part that impacts entropy. And so the closer this distance is to 0.5, the more the readings are random. And then again, the smaller the variance is in this distance, the more the readings are random.
So this is like the graph, like a 1 point for, or 1 count for every pair of
every pair of irises, exactly.
Of individuals, or pair of readings from individuals, or something like that.
So for the right side of the histogram, this is like basically you take every different person irises and then you compute the Hamming distance between all the pairs and then you plot them on the histogram. Yes.
For one reading per. Is it?
Yes, for 1 reading.
I see.
But the left is all readings of a single
Same person. Yes.
For many different people, 2 readings from that person.
Yes.
Thanks.
All right. And so basically you fit the binomial to this unlike distribution to get the entropy here. And if you trust me and plug in the numbers, this will give you about 249 bits of entropy that I just told you about from the old paper. So this whole calculation is actually a heuristic. And it has to be heuristic because accurate estimations requires 2 to the power k times k samples, and we don't have even close to that many biometrics to even do this estimation, which is why we need to use this heuristic. And we have used other heuristics like the NIST heuristics, and the reason we picked this heuristic was because this gave us the least numbers or the lowest entropy, and it's better to be pessimistic than being optimistic.
So do you have some intuition for like what entropy means in this context?
It's a really good question because like Amey will talk about feature extractors in a second, but there's some like task of there's information in the image and there's noise in the image. And here almost certainly we're measuring a little bit of the noise in there, but we have to remove some of the noise to get the information out. And so you could, for example, try and measure how much information is in the image, but that seems like the wrong thing to do. So, I mean, roughly what we're trying to get at is, how how many people would have to be produced? Sorry, how many people would have to be born before you have somebody who has the same distribution for like readings as somebody else's? That so it's something kind of stronger than like the false match rate for people, but it's close to that. So like this histogram looks much wider for fingerprints, for example, than irises. Just because there doesn't seem to be as many like
much information to actually play with to create entropy.
So can I think of it as like if I took all the if I could take all the noise out and get like, you know, your exact unique iris scan, then I'm looking at sort of like, I guess, the entropy in that distribution.
Yeah, and I kind of think of it as like this is nearly how many independent features we can produce. Like we know, like ML roughly knows how to give you like each pair of features is independent and each like triplet of features is independent. But this is like, you know, this is roughly like the number of independent components we think exist in this distribution.
Thanks.
Yep.
So just a question. So is the point here that there's a gap between these two histograms? Is that like?
Yes.
That means that you can use this, basically. Right.
Hopefully,
yes.
Right, like this is actually a major problem. Is if oftentimes if you want true accept rate of like 98, the tail for the white distribution will be overlapping with the black distribution, and so like there becomes an inherent trade-off between like accepting bad readings and rejecting good readings.
Right. So so like what is the? Is it like the false accept rate or true accept rate or whatever here? So I guess the diagram depends on the histogram depends on that, right? So it's fixed here, or
so we're gonna have to pick a distance for the cryptography, but that's gonna vary between security and true accept rate.
All right. I'll continue. So like I said, you know, this whole regime where you have no security when you're trying to correct more errors than entropy is actually unfortunately true for iris code as well. So, you know, the iris actually has more errors, about 300 bits of error, than it has entropy, which is 250 bits. And so it turns out there's no fuzzy extractor that actually works for the strongest known biometric to man. And this is also with the assumption that perfect code exists, which we don't know if they do. So this is actually even worse in reality. So does this mean all these fuzzy extractors are kind of not usable to secure biometrics? And the answer is fortunately no, because while we can't control what nature gives us, which is our irises, our fingerprints, or faces, we can manufacture certain things like puffs, which can be designed to be IID. And so if you're like, if you're designing puffs, this is surely fine to use. But as you have noticed,
say really quickly what puffs are.
Physically unclonable functions. So basically a chip that you produce that you can put in a phone device, for example, that's unique to that phone device. But as you notice, this talk is all about biometrics, so I'm not going to talk too much about it here. And so remember, our primary issue comes from the fact that you need to write down more information for redundancy than there's actually entropy in the whole biometric. And this is just how error correcting codes fundamentally works. In fact, these issues exist with any informationally theoretically secure constructions, like, you know, the ones I have listed here. So maybe let's look at other constructions with computational security. So here you can have many constructions. So for example, you can have a construction based on general gray box obfuscation from multilinear map, which is basically too inefficient to use in real life. There's also this construction using continued fraction decoding problem called GZ19, which is actually fine and fast enough if you actually trust the number theoretic assumption that this construction uses. And there are other error correcting codes with computational security, like with random codes or place in exponent, which unfortunately are really not usable for biometrics because they use random codes which actually limit decoding. And then finally, I'm going to talk about sample then lock, which directly encode information set decoding into computational techniques. And this is the construction I'm going to talk about today. All right, so let's talk about sample then lock. So here's the idea behind sample then log, which is that the bits of irises are correlated, and so you can subsample them to produce high entropy strings. And then you can use these subsample strings to encrypt the key that you're going to do cryptography with. And this does not require any error correction. So you can actually encrypt any distribution without the helper leaking information, because the helper doesn't really have any useful information for the adversary to really exploit. And I'll talk about how this scheme works now. All right, so let's talk about the gen algorithm here. So what you're going to do is, let's assume our biometric is of length 9 bits, for example, right now. So now you're going to get random combinations of the symbols from the initial iris reading or the initial biometric reading. So here I have sample positions 129, 359, 345, 567, 278 at the bottom of the screen. Now I am going to use the bits at this position as combination for the lockers that I have placed down there. So I'm going to take the key that I have generated in gen, which is like a random key that I've generated using a pseudorandom, PRNG or whatever. I'm going to take this key and I'm going to put this exact same key in every single locker. So all these lockers have the same key, and I'm going to use the bits at these positions to log these lockers. So here the helper value would be these logged logs themselves and the positions of the symbols that I'm going to use to unlock. So when I say positions, I mean like what position in the bit string, not the bits themselves. And then I'm going to use this to log the locker. Now I'm going to talk about authenticate. So how do I authenticate using this scheme, which is again pretty simple. So let's say I have a second reading of my biometric called final. And here at position 2, position 4, and position 7, the bits are different from the initial reading that I used to log these lockers. So now, as you can see, I can't unlock the first locker because my bit at second position is different than the one that I used to log this locker. And I can't do this for the locker 3, 4, and 5 either, because again, at some position, there's a bit that's different from the initial reading that was used to lock these lockers. But fortunately for us, there's one locker, which is the second locker, where all the bits I have matches the bits at the initial reading. And so I'm going to take the bits from my final reading, and I'm going to use it as a key to unlock this locker. And remember, since we stored the exact same key in every single one of these lockers, I'm going to get the key that I can use to do cryptography with. So now there's this trade-off between two goals for these combinations, which is, these lockers should be big enough that they can't be guessed, because right now I just have 3 bits in the locker, which is like very trivial to guess. But if you have like hundreds, that becomes hard for adversary. But also small enough that they can open for the correct biometric, because as I increase the number of positions in the locker, it gets harder. It gets more likely that there's going to be some position that I can't match. And as long as there's just a single bit that doesn't match, I can't unlock the locker.
So do you assume that you can tell if you can unlock the locker or not?
Yes, and I'll talk about it in a second.
Oh.
All right. So implementing this is like really trivial. So all you do is you hash the bits at these positions that you're using. So like, for example, the bits at position 359, and I'm going to XOR it with the key, and I'll add these check bits, which is like a bunch of zeros that basically tells me if I unlocked it properly or not. And this whole thing is secure in the random oracle model. And you get many perks for free because this is such a simple technique, because again, hashing is fast. It's like half a cycle per byte on Cascade Lake with Lake 3. And then for many platforms, hashing is already built into hardware like ACE, NE or something, which makes it even faster. And simple implementation means that it's actually harder to make mistakes, because what really cryptography struggles in the real world is making implementation mistakes. And there are already lots of libraries that can help people with building this. And finally, I would like to mention, people are already using hashing in the real world, even if they don't work with security. So this is something people are already familiar with and less likely to make mistakes. Now, you can actually go one step beyond. Like I said, this is secure in the random oracle model, but this whole thing is actually called a digital locker. And you can actually even improve the security to something like a standard model, although that's slightly more convoluted, and Ben can talk more about this, but you can definitely upgrade the security from random oracle model to whichever model you want that a digital locker works in. All right.
Can I ask a question?
Yes.
So is the helper data usually stored on the server and then sent to the client when they're attempting to log in, or does the client keep their own copy of it?
So the whole time for the whole thing, we actually assume that you're doing on-device authentication, which means that it's stored on the client, but it's on the client device. But yes, if you were also doing it interactively with a server or a machine, then yes, you can do it either way. You can keep it on your machine, or you can get it from the internet or from the server, whatever. Because this is supposed to be public, because it's just the positions and the locks themselves. And as long as you don't have the right bits, you can't unlock the locks, and you can't really do much with the positions as an adversary.
Is there?
Yeah,
Right.
sorry,
go ahead.
let me, I'm wondering if like there's an adaptive attack, right, where the server can change these ciphertexts because they look malleable, you know, so
Yes.
is that in the model, or?
So we don't consider it, but the reason why, so there's a separate thing called a robust fuzzy extractor, which is a bad name. It's really a non-malleable fuzzy extractor, or like a CCA security fuzzy extractor. In the random oracle model, this is, you know, relatively simple, as you might expect, right? You use the key you derive as a MAC, introduce this as well, and you check that before you like output the final key. So the reason we didn't do this is that like upgrades for robustness are known,
Okay.
and there's like generic techniques to do it. Yeah, so it's absolutely something you need to worry about, but we roughly know how to do it.
Yes.
Okay. Thanks.
Right. So I just talked about these trade-offs between two goals for combination, which is that these combinations should be big enough so that they can't be guessed, and small enough that they can open for the correct biometrics. And so it turns out prior work has not been able to achieve cryptographic security on this trade-off. So now I'm going to talk about ClearEyes, which is actually an integrated feature extractor. And just to not get people confused with the terminology here, a feature extractor is just something you give the image to, and it'll extract the bits from it so that you can actually do cryptography with it. And then we build a new fuzzy extractor that's a slight upgrade of the fuzzy extractor I talked about to do cryptography with. So we build a new variant of sample and unlock called Zeta then unlock. And so a few slides ago, I talked about how the bits of irises are correlated, which makes sense as they are not independently and identically distributed. Because if they were, and you have a bit string of 1024, it would have 1024 bits of entropy. But clearly it has like 250 in the dogman example, for example. And so what if we use this to our advantage? So instead of sampling randomly, we sample with an objective in mind. And so we still randomly pick positions, but we give extra weight to certain positions such that we are going to favor the positions that are relatively more error-free compared to the other positions in the same class, like the same person's biometric, whereas we favor positions that look random when compared to irises in the different class. And so basically, this is...
Sorry, I just want to say one thing there.
Yeah.
So everything we do here, when we're talking about statistics, we're not talking about statistics of people that we're actually going to use here. So this is like part of our training data set where we're going to compute statistics for this. So like if you do this on the people you're computing a fuzzy extractor on, you can do much, much better. But then your fuzzy extractor, you know, depends on the actual like statistics of the person you're trying to lock. So these are like global statistics over the population of irises.
I suppose if it were tailored to each person, then there might be some leakage in the helper data or something like that. Is that the idea?
Yeah.
Yes, exactly. All right. And so do this, we follow a really simple process. And I say this is non-trivial in the sense that you actually need to design ML that actually works for this. So if you train a normal feature extractor and then hope to do this, it will actually not give you any fancy results. So the process is really simple. So like Ben said, you carve out a portion of irises that we call W stats, and we don't use this for computing TAR or anything. This is like something we keep out again to prevent any kind of leakage from happening. And then we build a table for all positions of the bit vector that represents the iris. So for example, let's say your iris can be represented by 512 bits. You'll write all the positions from 1 to 512. And then for each position in the same class, you will calculate the probability of bits not being the same. So here, for example, at position 1, I have 8% chance that for all my W stats irises, there's 8% probability that the bits do not match. And for each positions in different class, I calculate the probability of bits being the same, which I call random. So there's again, for position 1, there's a 49% chance that, the bits are actually random. Now, obviously, between 1 and 2, I will pick position 1 because it has the least amount of error and it is the most random. And so this is basically how the weighted random sampling works with some tweaks. Okay, so now I'm going to talk about a few bugs that actually makes this idea not work as well as it should, and actually made our life a lot difficult.
Maybe
So
one quick question. So does this take care of correlation in any way, or is it looks like it does, it doesn't explicitly, right? Okay.
it definitely does not take care of correlation completely. I mean, the point is, like, do we try as much as we can to take care of the correlation? And in fact, I'll talk about it in a little bit why it doesn't. But yes, it does not completely take care of correlation.
But
So
like,
it's more like it's. Oh, go ahead.
well, right. So this is like feature quality more than anything.
Yeah.
We tried, or Amey tried, I guess I should let him talk, to do what you said, which is like look at the quality of pairs of bits and triples of bits. Yeah, so we tried to do this. Unfortunately, like the correlation seems to be above where you can do like the combinatorics exhaustively, but Amey will tell you the solution because it's exactly what.
Yes.
But so with this thing, you could have like the same bit repeated 100 times, and it would look like that was 100 awesome bits. Is that?
Yes.
Yes.
Yeah.
But I guess that gets somehow that's okay. Is it?
No, we do deduplicates. We don't use the same bit every time. We randomly we randomly pick them and then we deduplicate to make sure it's not the exact same bit every single time. Yeah.
But you're counting on the machine learning and the entropy test to take care of that.
Yes.
How does the entropy test help with
Because
that?
if you have the same bit repeated, it drives up the variance.
And that gets rid of the entropy.
Drives up the variance. Is that in that last chart, or is this something that comes after?
So remember Amey showed you those like histograms?
It makes the histogram and light distribution wider, and what that means is that it just reduces the entropy or the entropy test.
I see. Okay, so you're both doing the selecting of these bits, and then also you're trying to select the bits in such a way that your entropy test is good.
Yes,
is that,
exactly.
I see.
Yeah.
I see. Does the machine learning do optimize on both, or are those like two separate steps?
Yes, so we will talk about that in a second.
Okay,
Yeah.
okay.
So we do build some machine learning to take care of that for us.
Okay.
All right.
Thanks.
But before that, I'll talk about a few bugs. So it turns out that binary entropy might not be the correct heuristic because it's a bit too optimistic. And with this kind of stuff, it's better to be pessimistic. And the reason we were using binary entropy initially in our work was because all previous work uses it. So Dogman uses it to calculate the entropy. And then SSF19, which is like the previous version of the paper that actually built a system that does both feature extraction and fuzzy extractors, also used it because, again, Dogman used it. And obviously, it's better to be pessimistic than optimistic. So maybe binary entropy is not the right idea. So maybe we should switch to average min entropy or min entropy. And again, average min entropy is also not the correct heuristic because, if we have a bunch of loggers with a lot of entropy, again, you should expect that the adversary is going to target the one with the least amount of entropy. And so, it doesn't make any sense to use average min entropy either. We should just use minimum min entropy, which is like the least entropy you have, the logger with the least amount of entropy. And let's switch to that. So it should not be too bad. And that's what we thought when we were trying to switch to this. And no, it was really, really, really bad. So in the initial version of the work, we had about 80 bits of entropy, which is less than ours currently. But we were really excited back then because, previously we had like 25, 30 bits of entropy that was best in the literature. And we were able to spike this up to 80 bits. But it turns out when you switch from binary entropy to minimum min entropy, you also kind of change this, like the part of the fitting the binomial for the entropy test, where you use a min entropy now. And as you can look at the bottom of the screen, the binary entropy of 0.40 is 0.97, which is not that far away from 1, because this is multiplied to our figures. So this actually, so like the less it is, the more it impacts the entropy, whereas the min entropy at 0.40, which is where our unlike distribution was centered at, is 0.73. So what this means is that we essentially lose like 20-30% in our entropy just by switching from binary entropy to min entropy. And in fact, there were more things that happened that basically impact our entropy by half. So we went from like 80 bits of entropy to like 42 bits of entropy, which was really demotivating because we went from on top of the world to like back to the kitchen, I guess.
So is that, I guess, are you saying that the previous like work gets less entropy than they claim because they're using the wrong
So what I'm
measure?
saying, so we had so for context, we have like 5 versions of this work on eFriend. So the first version of work was completely incorrect. So then we came with the second version of this work, which was the one I was talking about before, where we had 80 bits of entropy. Then we fixed all these bugs because, again, binary entropy and average mean entropy were not the right target, and it's better to be pessimistic. Then became the third version of the work, which we went down to 42 bits of entropy. And there's also the fourth version, which I won't talk about because that just still, I'm traumatized about it. And the current version is the fifth version that we're showing.
But the one we were building on, there was actually a concrete attack.
Yeah.
So SSF19 assessed the average min entropy of subsets, and this ZCY21 picked the lowest entropy one, guessed that, and then hill climb to all the rest to recover the whole biometric.
Okay.
Yeah.
So
Okay.
you really do care about like the weakest one.
Yes.
Mm-hmm.
And which is why we actually switched from SSF19 or from average min entropy to min entropy. And in fact, CFP plus 16, which is the original sample and lock paper, also used average min entropy in their proof, which was wrong. And then we fixed that proof in our paper. All right. So after all this,
I'm kind of curious. How does the hill climbing attack work in this?
So basically, what they do is they assess the entropy of all the subsets. Like they sample a bunch of subsets, assess the entropy of them. The lowest entropy one, they produce realistic looking biometrics, sample those biometrics until they get a match. Then they say, I now know these positions of the biometric. And then they sample or then they guess other hashes that have a large intersection with those subsets, and they keep going until they get the whole thing. Right. So usually you want to think of like a biometric of 1,000 bits long, and we have like hundreds of thousands of subsets. So like if you have the computational time, bits are way over determined. So there's a pretty good chance that like there are two subsets that share 10 or 15 bits.
Yep. All right. So before I go further and talk about the fifth version of the paper where I fix all these issues, I'll talk about why this impact was so bad for us. And so, we rethought everything, and we were like, why did our sampling fail? Did it fail because, this whole idea of sampling multiple positions to find correlations just does not work? Or is it because correlations are actually just not pairwise? They can exist between 20 to 30 bits. But even if that is true, our current strategy does not work, because if you look at the number, just to do 10, 24, choose 5 with my estimated time to do it would take me about 167 years to just sample, which is, maybe if I was of a long living race of 1,000 years or something would be fine, but, that's not true. So maybe approximation is actually a good idea. So maybe we don't need to get this exactly. Maybe we can do approximation. In fact, maybe we can just do this during the feature extraction process using ML, and it can give us a nice approximation where we don't have to worry about this. Now, before I go further, I will mention that the results from this technique are actually not useless because interestingly enough, it creates a gap between average min entropy and min entropy. And while this is completely useless for current work because we have to focus on min entropy, there is some concurrent work that we are currently working on, which actually exploits average min entropy. And in that kind of space, this actually will be pretty effective. But that's for the future, so I won't talk about this right now. All right. So let's build a feature extractor that does zeta sampling, which is, again, really simple. I won't talk about it in too much in detail because, there's a lot of annoying stuff. But the whole idea is that you take the embedding, so you basically take the embedding, so the floating point values from your model that you were using as the bits basically to do this whole process. And then we apply a custom loss that just has this one task to reduce the error between embeddings of the same person and make it random between different people. And then Basically, it creates refined embeddings with this strategy in mind. And it's not really complicated. It's like really simple. But this simple technique actually helped us quite a bit to get a histogram that looks like this, which is actually really fantastic. We're so happy with it that you can see Ben's message down there where he says language because he was mad at the language I used after that histogram. And I'll show you what that histograms mean in a second. So with this feature extractor, with this technique, we were able to get rid of a lot of the correlations as just to answer Melissa's question, which is, at a length of 115, we were able to get 105 bits of entropy. So there were basically only 10 positions of correlation that's left in the feature or in the features themselves. And in fact, this is so good that we don't even need to do zeta sampling after we reach this process, which also saves us time. And this gives us like above 100 bits of entropy, which is fantastic from what we were at before, which is like 42 bits and so on.
So you're saying like instead of building that little chart with the different positions, you're sort of
just tell machine learning, please do it. Yes, yes.
I see. So sort of implicitly doing it inside as part of like optimizing that.
And the good thing about this is it can simultaneously do what features are good and how correlated are they.
Yes.
Mm-hmm, mm-hmm.
And effectively, I think it kind of works as well as it does is because when we're doing this sampling process, we have to convert because like a CNN just outputs floating point values which we can't use, so we convert them to bits by if it's greater than 0 we make it 1, if it's less than 0 we make it 0. And when we do that, we lose a lot of information. But here, this information can be used internally inside the feature extractor to basically do its best in doing. All right. So for our evaluations, we have these subsets of size 115, where k is the length of the locker. And then we, instead of like having 5 lockers, like how I had these 5 locks at the beginning of the talk, where I showed you 1, 2, 3, 4, 5, we have actually 250,000 lockers. So there's high probability that at least one of them will unlock. And they have a minimum entropy of 100, and they have an average entropy of 106. Again, we can't really care about average entropies. We can only care about minimum min entropy. So that's actually 100. And so it turns out that with 250K lockers, our weakest link is the locker with the minimum min entropy. So is there an optimization we can make to like slightly bump this up a little bit? And for this, we have this technique called cutting the tail that we use, which works by getting rid of the worst lockers. And so we write down the lockers with highest entropy, and I'll show you how that works. So for example, let's say we have 5 lockers with entropy, 3, 2, 2, 1, 3. Again, adversary would,
So are the positions the same for everybody, or are they sort of different for each?
Yeah, they're same for everybody, exactly.
I see. That's how you can pick bad ones.
Yes.
Is there a reason to do that versus having a special, like picking a random selection? I guess maybe this thing you're about to explain is, but other than that.
Well, but the entropy test needs statistics, right? So if you picked random positions, you could have chosen really poor ones. So you need some way of like knowing, did I pick good positions?
I see.
Yeah.
Mm-hmm.
Right. So here I have this one locker with entropy of 1, and obviously evil courage is going to target that one locker and unlock it to get my password. So how about I just get rid of that locker? So that locker is gone. So now courage will target the locker with the second least amount of entropy, which is like the one with 2 bits of entropy. So again, I'm like, okay, I won't let courage exploit that. I'll get rid of that locker. So I get rid of that locker. And now I have 3 lockers left. Again, 1 with 2 bits of entropy. Again, I don't want courage to exploit that. I'll get rid of that locker too. So now I'm satisfied that, okay, I'm happy with courage doing 3 bits of work. He can do whatever he wants now. And unfortunately, again, this has a trade-off that since you get rid of number of lockers, it lowers TR. Yes.
So maybe an obvious question, but if you're already doing this like fixed subsets and then reducing the bad ones, why not pick way more to begin with and like just find the very, very highest?
Yeah, you can do rejection sampling too. Yes, if that's what you're asking.
Or you could even what you said about people picking your own. You could publish 100 million good subsets, and then people could randomly pick them.
Yes.
But why? I guess why do you do 250,000 and not 100 million? Like what's
so the reason is for performance. So we have this target of authenticating in a single thread in 1 second, which is why we have 250K. You can have as many as you want. if you
But
are
I thought-
fine with the.
Yeah. But what's actually going to happen in the authentication is just the ones that aren't blacked out, right?
Right.
So then
Yeah.
couldn't you run like for a really long time, try way more subsets and then just find the best ones if you
Yes.
had more? And that would be just in the algorithm design step, right?
Oh yeah. Oh, totally. During the
Bunch of-
searching process,
okay,
you can
okay.
run it as much as you want. We just didn't want to do it too much because then
But we're on an academic budget.
we are an
Okay,
academic
okay,
budget. Yes,
okay,
yes.
okay.
Absolutely. Right.
Okay.
Like this is a global thing that can be done ahead of time.
Yes.
So you can put as much time in as you want.
I see. Okay, cool. I wasn't sure if there was some other downside to doing that. So
Yeah. No.
yeah.
Well, sorry, there is a fear that the higher entropy a subset is, the less probability there is of it unlocking. Right? So that if you only take really high entropy ones, you're never going to have good tar. Turns out that's not true, but it's a fear.
Okay.
It's a fear.
Okay.
And the reason it lowers char again is because you went from having to unlock 1 out of 250k lockers to 1 out of 200k lockers. So it does not impact char as much as you would think, but it does impact a little bit, like maybe I think it's like to 1% or something, which is like nothing really. Right.
Thanks.
So I'm going to talk about one final optimization which is called enrolling multiple lockers, which is that, hey, instead of just using one image to enroll and then one image to authenticate, you can actually enroll a bunch of images at once and then authenticate with a bunch of images. So here, for example, here I have Courage, who's watching his phone, or he's sad, or he is or he's sitting down right now, he's kind of sleepy. And then I enroll all of these biometrics to the machine. And again, even though they look like they're in different time steps, you can also expect them to be like a video where I cache like 60 frames and then I put them up all on the server for enrollment. And then I can also, again, take a picture or take a video of my face or iris and then extract all the 60 frames and then authenticate with them and then make sure as long as one of the pairs between enrollment and authentication authenticates, I win. I can unlock my device. And this actually does quite a bit in boosting. And part it does so well is because, we use academic data sets because, we don't have a lot of data sets for biometrics out there. And, the data sets themselves have serious quality issues, which is why this technique works better than it ought to in the real world. So in our case, it boosts the TAR up by 28% for the IITD data set, which is the one we use for all our stuff in this paper. And with this technique for 83 bits of entropy with 3 authentication readings and then 2 enrollment readings. And the reason we have 3 and 2 is because, again, academic data set, it only has 5 images per person. So, we just did the best with what we had. If we had more, I don't have some results here, which I kind of removed. But, with Notre Dame, they come with like 20,000 images. But again, Notre Dame is also a lower quality data set. So that's why we don't use it. We can get you like 100% TAR at like 128 bits of entropy, but again, we don't really talk about it in this paper. But yeah, for 83 bits of entropy, you have 98% TAR, and for 105 bits of entropy, you have 92% TAR. And this takes less than a single second to authenticate with a single thread of M4 processor. And limited data gets us good results. But like I said, at higher quality, at lower quality, at higher numbers, we can seriously upgrade this to about, like I said, like we can get you 256 bits of entropy at like 95% TAR with ND, but that requires also like 50 readings, which is quite a bit. Also, I would like to mention, this is an embarrassingly parallel problem. So what I mean by this is that you can actually use multiple cores to speed up this time. So let's say you are using an iPhone, which has like 6 threads. You can basically slash the time by almost like 4 or 5 times. All right. Now, I'd like to talk a little bit about future work. So I think we have closed the problem for irises, but there are other biometrics where this is not the case. So right now, with our own feature extractors, for fingerprints, we have 44 bits at entropy at about 60% TAR. And for faces, we have 59 bits of entropy at 60% TAR, which is a lot lower than the 105 bits number we have given you. We have some current work that can actually bump up this entropy for fingerprints to be about 73 bits at like 90% TAR. And for faces, it can bump it up to about 84 bits at, again, 90% plus TAR. And so for that, we designed a new new fuzzy extractor with a startup called Dapple Security, which works very similar to how hardening works for like passwords, something like Argon 2 or bcrypt. so it's a fuzzy extractor that kind of works similar to how Argon and Bcrypt works, but for biometrics. And we are also building a new interactive protocol that's working on that's built on BMT25, which was also published alongside this paper at CCS, where we take this from the non-interactive setting, which all this paper was really about, to the interactive setting where you have a server and a client. All right, happy to answer any questions.
I have a question about the previous slide.
Yes.
So the
Can we first do like a thank you to the speaker?
sure.